Here is our presentation on organic flexible electronic devices. This is a general outline for the presentation. Organic electronics are electronics that are made of polymers and small compounds that are carbon-based. The interest in the field picked up in the late 1970s when the polymer polyacetylene was found to be electrically conductive, a Nobel Prize-winning discovery a few years later. With time, research showed that some polymers can have electrical and optical properties of insulators, semiconductors, and metals, given certain doping concentrations. This allows for impressive tunability properties for the materials. This works by taking advantage of pi bonds in polymer chains to allow electron flow. The general scope of conductive variation is displayed in the chart above. Some of the major opportunities of these materials are that they're made of abundant elements. They can be printed, the materials are biocompatible, and the flexibility that they allow. The abundance helps in replacing rare earth metals, which are at the bottom of the periodic table, with more nonmetals in electronics, desiring elements in the top right, namely nitrogen, carbon, and oxygen, which allow more access to these resources. Printing benefits by reducing costs and allowing for large area substrates through methods like screen printing and inkjet. Biocompatibility is important for medical applications, as the harm from biological interaction is greatly reduced. Flexibility is essential, as it improves durability from a lighter and thinner material that can bend within reason. This is a result of a low Young's modulus that's found in organic materials. Organic flexible electronic devices are a group of electronic based on organic thin film devices to meet the rising demand for flexible appliances. This doesn't come without challenges, however. One of the primary issues with OTFs is the compromise between better flexibility and electrical traits. As well, due to the thin film nature, the desired manufacturing process is to print the materials, requiring the accuracy of the printers and the ink compatibility to be considered. Regarding the organic materials, they are vulnerable to normal environments, so they are typically coated with a protective layer. An example of a vertically stacked printed CMOS circuit is shown, which is only a micron thick substrate. Organic thin film transistors have a wide variety of uses in the future of medicine. For invasive procedures, everything must be sterile. Heat-resistant OTFTs have proven to be able to withstand medical-grade sterilization procedures, which gives feasibility to the common use of OFEDs in operation where a device needs to be inserted into the body of an organism. Additionally, the organic nature of the device means that they are more biocompatible. This is important as it allows the device to stay safely in the body for longer periods while being harmless to the patient. The image depicts the concept of an intelligent catheter that takes advantage of OTFTs to measure the spatial distribution of pressure after it has made contact with an object. The highly flexible OTFTs are visible as the gold and white colored tubes. The non-invasive future of OFEDs in medicine is making unconscious devices, which the patient will notice less. Devices such as sensors and actuator arrays can be placed on the skin with little to no irritation due to their organic, lightweight, and flexible properties. Future uses, for example, could deal with minor insole pedometers powered by piezoelectric energy, although a more life-altering change would be OFED-based surface electromyographic sheets, which could improve the rehabilitation time of prosthetic patients. as well as ultimately improve future prosthetic design with electronic skin, which mimics natural skin, but can also be made to display things like the wearer's heartbeat. To achieve this, it is imperative for the material to be flexible and withstand mechanical deformation without losing its electrical properties. Aside from just medical benefits, OFEDs have a promising future in consumer electronics.
OFED consumer applications. One major use for OFED technology in the consumer world is the OLED technology. These OLED screens are known to have the best color accuracy as well as the best black for a screen, whether it be mobile or for a TV. The OLED, or organic light emitting diode, will have almost a perfect green, red, and blue, as shown from the graph in the top right. These screens will also provide some of the best viewing angles while keeping their color accuracy, as shown in the bottom right figures. In the bottom right figures, the x-axis is the viewing angle. The y-axis we could call the color accuracy or color performance. As you can see, the graph for all three are relatively consistent, going from 0 degrees to 80 degrees. So your viewing performance, whether you're in front of the TV at 0 degrees or off to the side at 80 degrees, will be relatively the same. So you will not have a loss in performance. These OFEDs have also made it possible to create curved displays due to their flexible nature. This can be done because there is no backlight required, like in a liquid crystal display or LCD display. These organic LEDs are self-emissive, which means that the OLED panel can be attached to many different types of surfaces, whether they be curved or flat or clear. The figure to the right is the layout for an OLED display. The red, green, and blue layout is shown. The history and creation of OLED technology. The first OLED consumer product was developed by Pioneer in 1997 for the front panel of one of their head units. After that, the technology was implemented in the cameras, cell phones, GPSs, radios, and more. One way of creating these OLED panels is by thermal evaporation. This is done in a vacuum, and it is more precise because the thickness can be monitored more closely. The second method is by spin coating. While this method is used to create polymer LEDs, this method is less precise because the thickness cannot be closely monitored. That is because each layer for the spin coating is added on, unlike the thermal evaporation. With either of these methods, the goal is the same: to create an OLED panel such as the one shown to your right. The image shown to your right is the desired layout or design for the panel to create optimal light and picture. Disadvantages of OLED technology. A known problem that is talked about amongst consumers is that OLED TVs have a burn-in tendency. This burn-in is caused by the discrepancies of the red, green, and blue intensity, which will cause image persistence. This image persistence could also be considered burn-in, as these OLED panels are sensitive to UV light, where prolonged exposure will cause dim or dead spots. For example, if you were to leave your TV or OLED TV out in the sun, you would see dead or dim spots after a prolonged period of time. Or if you used a UV laser or a Blu-ray laser, you would instantly begin to see dead spots or dim spots in your TV. Lastly, the life expectancies of the red, green, and blue films have varying lifespans, which will cause image distortion over an extended period of time, as shown in the figure below. In the figure, it shows the efficiency and lifetime. The lifetime of the red filament is 80,000 hours. The green is 40,000 hours, and the blue is 7,000 hours. With this being said, you can see that the OLED TV does not have an extremely long lifespan or runtime compared to other TVs. With all that being said, OFED products do have their great attributes towards solar energy.
Solar applications. Similar to consumer electronics, the desire for thinner solar cells has grown recently. However, making solar cells smaller in area wouldn't be ideal, as output current is directly proportional to the area of the cell's surface. This leaves scientists with less options to minimize footprint. An answer to this is the use of organic photovoltaic semiconductors that can be made into thin films to change the solar cell's dimensions and characteristics. In the end, what you will have is a cell that is more light and flexible than silicone cells. In the top right picture, we have an image of a silicone semiconductor solar cell, and on the bottom right picture, we have an image of a organic photovoltaic semiconductor solar cell. Types of organic photovoltaic cells. Organic photovoltaic cells come in two different types, differing mainly in the active layer or semiconductor layer construction used. The first is based on small organic molecules, and the other is based on conjugated polymers, which are linked large molecules. These two methods are called bilayer heterojunction and bulk heterojunction solar cells, respectively. In this type of application, P-type organic semiconductors include polymers based on thiophene building blocks such as P3HT and PBTTT. The best N-type materials so far have been fullerene derivatives such as P66-1BM and PDI. One of the key challenges in organic materials is their inherently low dielectronic constant, resulting in a relatively short electron diffusion lengths compared to inorganic semiconductors. This means that freed electrons may pair again before they reach the acceptor, therefore making a cell less efficient. To improve the efficiency of the cell, the donor and the acceptor are both closer. This is shown in Figure A, the bilayer OPV. However, to get light absorption to free the electrons, it's required that the two semiconductors be greater than 100 nanometers apart. This 100 nanometer spacing is shown in Figure B, where in Figure C, we have what a real BHJ will end up looking like. In conclusion, organic flexible electronic devices have certainly caught the eye of many admirers in the world of science. Its thinness, flexibility, and its minimal cost all have the world in high hopes for its continued success. This polymer-based semiconductor started out as an alternative to the well-researched silicone, but it was slowly realized to have properties that could replace it in certain applications. This is due to its compatibility with a multitude of substrates and chemical tunability. Although all FEDs have shown potential over the years, it still has a ways to go to replace silicon in some applications. For instance, in organic photovoltaic cells, efficiencies have been recorded to be 2.5 in 2001 when it was first begun to be researched, and 17.4% in 2019, the past year, while in single crystal silicon, 13% efficiency was recorded in 1980 when it was first begun to be researched, and In 2019, it was recorded to have an efficiency of 27.4, which is relatively 10% higher than that of the organic photovoltaic cells. So as you can see, there's still progress to be made before photovoltaic materials can replace silicon.
We would like to give a huge shout out to the following citations that we used during this PowerPoint.